do this. Okay, so here's our shape, and we have to give a couple pieces of information to talk about what we're doing. So I'm going to write the instructions off to the side here. Let's dilate. We're going to dilate that figure about, we have to give a point of dilation. Remember when we did rotations, we had to rotate about a point? With dilations, we also have to dilate about a point. And I'm going to say for this first one, let's dilate about the origin, the point 0, 0. And we also have to give it a factor. We're going to do a factor 2, factor 3, factor 5. Let's do, I think 3 is good. So with a factor of 3. We're dilating about 0.0, with a factor of 3. Sometimes they call this a scale factor. Sometimes we'll put the word scale in front of that. So after we do this, we are going to expect to have something kind of the same shape, but it's going to be bigger. How much bigger? 3 times as big. Okay. So there's a couple of ways you can do this. You can do it with a ruler, kind of like I was doing with the meter stick a minute ago, but that gets kind of tricky. It's a lot easier on grid paper to count. So I'm going to show you this. This is the part that people kind of struggle with. Do you need the handout? There's some copies of it right here. Sorry, does anybody else need a copy of the handout? Landon, did you get one? Awesome. You with us? Okay. All right, so this is the part where I really need your focus. Are you ready for this? Okay. So I'm going to talk about, first of all, draw me a nice big dot at the center. When we do a dilation, that center, that point that they give you is key. We always count from that point. Always count from that point. Can somebody give me instructions for how to go from that point to point A? If I asked you to give me instructions, how far to go, which direction to go, what would you say? Rise 2, run 3. So up 2 and over 3. Agreed? I'm going to draw some little dotted lines going up 2 and over 3. Up 2 and over 3. I like how you call that rise and run. You're thinking of slope. I can tell. You're trying to make a connection there with slope. And there is sort of a relationship here. All right, now when I go to A prime, I'm not going to go up 2 and over 3. Anybody want to guess what I'm going to do instead? What do you think? Up 6. Where are you getting 6 from? 2 times 3, right? Originally we went up 2, but now we're going to go up 3 times as far. So we're going to go up 6 and over what? What do you guys think? Over 9? Because we were originally going over 3, and 3 times 3 is 9. So let's try it. If I were to go up 6, so where are we going to start from? Where do we always start from when we're dilating? From the center. So up 6 this time. 1, 2, 3, 4, 5, 6. And then over 9, we said 1, 2, 3, 4, 5, 6, 7, 8, 9. And we think this is where A prime is going to be. Now, I showed you when we did our squiggly dilation on the board that we could connect the new point and the original point, and that line should go back through our point of dilation. See how that's totally doing that this time? All right. So there's A prime. How many of you guys think you'd be ready to go ahead and do B prime totally on your own right now? I got a handful of people that think they got it. Go ahead and do it on your own if you think you can. If not, watch me. I'm going to go over B prime. All right, so I'm looking at B here, and I'm thinking, how do I get from my center to B? I would still go up 2, but this time I'm going left by 1. So up 2 and left by 1. But I need to triple that. I need to multiply both of those by 3. So instead of going up 2, I'm going to go up 2 times 3, which is 6. 1, 2, 3, 4, 5, 6. And before I was going over 1, but I'm going to go over how far this time? 1 times 3 is 3. Good. So 1, 2, 3. And that gets me my B prime. All right. Could you guys go ahead and do C prime and D prime for me? I'm going to walk around and see how you're doing. If you've got a question, get my attention. C prime and your E prime. Anybody click on that prime notation? 3.1. 5 through 10. So 3 with all the homework problems. Looks good. You can go ahead and connect those dots and make your new shape. So mine minus C. All right, let me catch up to you guys here. C looks like I'm down 2 over 2, so I need to triple that. So 2 times 3 is 6. So I need to go down 6 over 6. Prime. And then D down 2 over 1. So multiplying by 3, that would be 2 times 3 is 6. So down 6 again. And instead of over 1, we'll go over 1 times 3 is 3. And Amir, thank you for the reminder. For those of you who are just joining us, I do have some materials over on this table there, and there's some rulers over there. If ever you feel like you would benefit from having a ruler, feel free to go over and grab one out of the open box on the shelves over there. All right, let's connect these up and make this shape. I'm not using a ruler, so mine might show up a little squiggly, but we can kind of get the idea. Not as squiggly as our rubber band ones. This is actually really, you guys did a really good job with that rubber band thing. Even a smiley face, usually it's like all over the place. So yours is a little lumpy, but like way less than normal. All right. I want to point out a couple of things. Well, I'd love for you guys to point out a couple of things. What changed? It got bigger, and we already talked about how much bigger. We think it's going to be 3 times as big. I could kind of count and look at the top of this. If this was 1, 2, 3, 4 units wide from A to B, then this should be 3 times that. This should be 12, right? Count them out. Is that 12? It is 12. Yeah. So everything is 3 times as big. In terms of, well, what's 3 times as big? Distances or angles? Both. Oh, we have an interesting conjecture there. Someone just said angles stay the same. Thank you, Abby. Is that true? Do you think the angles stay the same? Do they look like they do? Let me grab some tracing paper here and we can test this hypothesis. Conjecture. Sorry, hypothesis is science. So I'm going to go ahead and trace this angle A right here. What do you guys think? When I slide that up, is that going to match the other angle A up there? Oh, look at that. Perfectly. Perfectly matches. So the angles stay the same, but the sides are different. I'm going to take you guys in the way back machine here real quick. This is our chapter 1 packet. Ooh, that is not my chapter 1 packet. Anybody missed the chapter 1 packet? Oh, I might have it. Do you all remember when we talked about rigid transformations? Rigid transformations were things that preserved or kept 2 things the same. The size and the shape ended up being the same. Right? We said that reflections, rotations, and translations were all rigid transformations. We just added a new type of transformation. A dilation is also a transformation. Is it a rigid transformation? Rigid transformations keep the same size and the same shape. So it keeps the same shape, but not the same size. And shape is really determined by what? Alex, you were kind of saying this a second ago. Not by the lengths of the sides, but by what? By the angles. Yeah, the angles determine the shape. The lengths determine the size. All right. There is something kind of cool about coordinates with these. I'm going to see if you guys can make a connection for me. Could you please write down where we got a little space over here? A, B, C, D. And could you find the coordinates of those 4 points for me really quickly? Nope, the originals. The originals. Like A is at, what is A? Has an X coordinate of 3 and a Y coordinate of 2. So 3, 2. Make sure you're doing X and then Y when you do points. Can you find the coordinates for all 4 of those points really quickly, please? We'll practice writing coordinates. Make sure you take care of your positives and negatives when you're doing this. And once you've got that done, could you right next to those write me coordinates for A prime, B prime, C prime, and D prime? And I'm hoping that you see a pattern forming with these. Anybody seeing a pattern here? Say that again. Multiply what by 3? The coordinates multiplied by 3? 3 times 3 is so you're saying to go, to go from my old X to my new X? 3 times 3 is 9, and 2 to go from 2 to 6, that's also times 3? Oh, it is, totally. Does that work for all of them? So I don't actually even have to look at my picture to find these. I could just use these coordinates and multiply each of them by 3, and I would get the right answers. Check me on this, because you might have actually looked at the coordinates. I'm not looking at the picture. If I do times 3 and times 3, I'd get negative 3 comma 6. Is that what you got? You looked at the picture? Times 3 times 3, those will both be negative 6s. 1 times 3 is 3, negative 2 times 3 is negative 6. Did that work? Oh, that's a neat shortcut. Now the question is, does that always work? Maybe. Maybe is a good answer. We're going to do one more dilation in here. We're going to check and see if this works all the time. All right. I'm going to draw a point, a new point on my graph. I'm going to call it point P. I'm going to put it right there at 3 comma negative 3. Can you guys put that on your graph too? We're going to do another dilation. And I want to write down my instructions here. Where do I have some space? I guess I'm going to have to go up here. For this one, I'm going to dilate about point P, which was 3 comma negative 3, with a factor of, let's do a factor of 2 this time. And let's do it with counting, and then we'll see if the shortcut that we just came up with applies to this, okay? So I'm going to create a new A, B, C, D, but they're going to be double primes this time. We've already used up the primes. So same process. Remember, P is our center of dilation, so we're always going to count from there. So what's your directions to get me from P to A? How would you tell me to get from P to A? go up 5, right? We don't have to go over at all to get from P to A. So to get from P to A double prime, I'm going to do that, but I'm going to do it by a factor of 2. So I'm going to double it. So instead of going up 5, I'm going to go up 5 times 2 is 10. So up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is going to be my A double prime. All right, then I'll kind of think through, how do I get from P to B? Well, it's up 5 and over 1, 2, 3, 4. Up 5 and over 4. If I double that, 5 and 4 doubled would be 10 and 8. So here's my up 10. I already counted that out. Then to over by 8. 1, 2, 3, 4, 5, 6, 7, 8. We can get it here. Can you guys go ahead and do C and D for me? Always count from P. Remember, we always count from the center of dilation. Up 1 and over 1, 2, 3, 4, 5. 1 and 5. Both times 2 would be 2 and 10, right? So up 2 or 1, 2, 3, 5, 6, 7, 8, 9, 10. D is up 1 over 2. Double that would be up 2 over 4. 2 over 4. Interesting. It's a scale factor of 2. I was kind of thinking it'd end up being twice as big. Does that end up being twice as big? Yeah, I think it is. This was 4 across the top. The original was 4 across the top. And if I count, I'm pretty sure I'm going to get 8 across the top here. Now I want to see if this works. Remember the shortcut that we did down here? Does that work? Let's look at A. The original A was at 3, 2. And A double prime was at, where was it? 3, 7. Does that shortcut work this time around? No. So you said maybe. That was a great answer. Nice. Have you seen this before? Or but that's just truly a conjecture. Okay, and it's correct. It's correct. So this trick that we did where we just multiplied our coordinates, it is going to work, but it will only work in special circumstances. And Alex has made a correct conjecture, and it has to do with the point of dilation. If you dilate about the origin, that's going to work. If you pick a point that's not at the origin, so P was not at the origin's at 0, 0. If you pick a point that's not at the origin, that doesn't work. There's no shortcut for this. Okay. All right. So probably the first time that most of us have done dilations, paper and pencil. Could you guys show me on your thumb meters how you're feeling right now? If I gave you a little quiz and asked you to dilate some shapes on grid paper, where would you be at? Would you be like I kind of think I understand what I'm doing, but I might make some mistakes? I would 100%, or I have no idea where we're at. Where are we at? It's like we're in the learning zone. The learning zone is kind of in the upper half. Okay, some of you are like, I have learned this already. I know how to do this, and that's great. Okay, so I think it's time for us to get this into our packets. I think we got a space in our packet for dilations. See if you can find it. Is there a learning log for dilations? Oh, totally. Totally. All right, so what do we know about dilation? What would you guys put in here? These are your notes. What would you put in, Landon? Oh, you don't have to ask. If the pass is there, you can just sign up. And it is. Can you tell me one thing that you learned about dilations, though, before you go? Oh, you know what? All right, okay. What did you guys? What have we learned about dilations? It's always bigger. Now, it is possible for dilation to make it smaller. For now, you're right, though. All the ones we've seen are bigger. I'm glad you brought that up. That was a really good point. Remind me of your name again. Thanks. But by the way, those of you who just joined our class last period, you're going to want to give me like a month or so. I really struggle with names. Nate, can you guess what my scale factor would need to be in order to make it smaller instead of bigger? Could you give me an example of a scale factor that might make something smaller? 1/2, like 0.5 would make it smaller. If you pick a scale factor that's smaller than 1, it's actually going to make the shape end up smaller. That's awesome. Good for you. Okay, so you got an idea. What can we put on our notes? Okay, so size changes, shape remains the same. I think that's important. And that means it's not a what? Not a rigid transformation. So I think I would lead off with that. Not a rigid transformation. Rigid transformation requires the size and shape to remain the same. Zoe pointed out that the size changes, but the shape is the same. Listen. That's one of the facts. And then basically, from my point of view, the only thing else that we really learned was how to do it. And I don't know how you describe that in words. Anybody have an idea how you describe that in words? Would you describe it in words, or what would be another option that we could use in our notes? We could do a picture. Could you draw a picture that would show how to do it? Maybe an example? Maybe an example would be a good thing to put in. I like examples when I look at my notes. I like examples, and I usually like to have a couple of words that describe what's going on. So this is for me. You don't have to copy exactly what I put into my notes, but I'm going to make an example. I'm going to go ahead and draw myself XY axis. And I'll just tell you guys, a little spoiler alert here. When we do dilations, for most of this chapter, we're going to be dilating about the origin. So I'm going to make because I've been through the book before, because I know kind of the level that you're going to get to on this, I'm going to go ahead and make my example dilating about the origin, because that's most commonly what you're going to see. And I'm going to make my own shape. I'm going to make something simple. I think maybe a triangle. You want to do a square? You do a circle is going to be tricky. You totally could, though. You wouldn't technically have to do every point. You'd have to do the center and one of the points on the outside edge, and then you could kind of figure out what the rest of the circle would look like. I wouldn't do a circle personally, and not on my notes. That's a little complicated. I like my notes to be kind of simple case, right? And I can use a simple example to kind of look at a more complicated one. So I'm doing a triangle. You guys do it. I mean, it's your notes. If you want to do a pentagon, by all means, I'd be really impressed to see some pentagon. I'm going. Oh, what? Sure. Yeah. It is your notes. You do what you want. I'm just going to make a nice simple triangle. I'm going to get all complicated. That's cool. No, this is a key process, guys. I really don't want you just copying exactly what I have on the board here. I'd like you to make your own notes, because that's when you get into higher level courses, especially in math courses, your teacher's not just going to stand up here and say, copy my work. They're going to say, come up with your own notes. It's an important part of learning, is to be able to decide for yourself what's going to help me later on. You guys have been taking notes for a long time. You should have a pretty good idea about what's helpful to you and what's not. Unless you're never looking at your notes, which is a bigger problem. So you do what you want, but I'm going to go with say triangle. I think I'm just going to go scale factor 2 because I don't think I can fit any more on my grid here. Let's run out of room. You got an idea? What's your idea?
To calculate.
Oh, to describe in words. So calculate the rise over run and multiply each of those things by your scale factor. I love it. That's a great way to describe it in words. I'm going to steal that. So when we do it, I'm going to write how to, because that would draw my eye if I were taking a test and like, oh, I can't remember how to do this. And I look at my notes and I'm like, how to, like, oh, I'm saved. I really like that. I'm going to try and remember exactly what you said, but I might need some help. Calculate rise and run. And I would probably insert one really important thing in here. I tried to emphasize this a lot. From where? Where do we always start from? From the center of dilation, right? And the reason, you guys know why I'm emphasizing that a lot, what would you guess? Because that's where people make mistakes, okay? So always, always, always from the center of dilation. I'm even going to underline that part. And then you said, and then do what? And then multiply and just in case I don't remember what them is, I'm going to write rise and run again. By the scale factor or the factor, same idea. Oh, I love that. That's really good. I think I'd be able to read that and that would give me a good idea of what to do. Now I'm going to go ahead and finish up my example here so I've got a good visual of it too. Because I'm a visual type person. I like being able to see things, but I also like having words next to it that describe it. So remember when we do this, we have to give some specific instructions. So in my example, I want to write down what I'm doing. I'm going to dilate about, I'm going 0, 0 for my example, but again, it's your notes, you do you. With factor 2. And this is kind of something I stole off of. I was kind of poking around at other people's notes first period today, and I saw someone do something similar to this. So either work. Feeling pretty good about that. When I look at notes that I've written, I always try to imagine myself. I'm on a test. I try to put myself in the situation. On a test. And that kind of like rush of like excitement and anxiety when you're taking a test. And you get to that problem and you're like, I blanked. I knew how to do this 2 weeks ago and I can't remember now. What would I want to see in my notes to get me over that blanking thing? What's that? Motivational note. You can do it. Yes, that would be helpful, but I would want to see some good notes. And if I saw this, I've got a nice how-to, I've got a nice example. I think this would be pretty helpful to me. Now, some of you might not like having Like some of you might not be visual people, so you might not even include a picture. Maybe you just have a big description of it. Or the opposite. Maybe some of you don't like reading a bunch of words. You'd rather have a picture with arrows and that kind of stuff. We need to start getting to the point where we really understand how we learn individually and tailor your notes so that they're going to work well for you. I've got some extra space down here. I could leave this because we will talk about some more about dilations later. I might run across some other examples in my homework that I might be like, ooh, that would be really good to get in my notes. The other thing that I could put in here, and I'll let you make the decision yourself, we did this little shortcut thing. Would this shortcut apply to the example that I did? Yeah, because why? Because I did dilate it about the origin. So I could kind of show that shortcut in here if I wanted to. Am I going to do that? I think I would probably, for myself, I might choose not to do that because the shortcut doesn't always work. But this method where I kind of count and double it or triple it will always work. So I think I'm going to stick with the thing that it's going to work 100% of the time and not include the shortcut. Maybe at the end of the chapter, if I haven't filled in this other space down here, maybe I'll come back and use that shortcut if I find that it's really useful in my homework. But I think we got a good start on our notes here. All right. Okay, that's great. You guys did awesome today. That's going to be our notes for today. Yeah, you guys have some time to start on the homework. And that homework is going to be due next class, which is the 17th. And it's going to be 3.1.1. We're going to be doing problems 5 and 6 and 7 and 8 and 9 and 10. And that is all. That's only 6 questions. Probably all of them have like A, B, C, D, and E in them, right? Yeah, you got 25 minutes to get started on it, right? Some of you are going to finish this thing fast. You're going to need grid paper for the first couple. Where do you suppose you can find grid paper? The back of the handout. Yeah, look what I did. Trying to save trees. One-sided handout with graph paper on the back. There you go. If you don't have your own graph paper, use the back of the handout. All right, folks. Go ahead and get started. Let me know if you've got questions. Thank you for your attention. You did awesome.